Okay, and then share my screen to inch, and then make my VS Code real big. Is this size fine for anyone who's like watching from a computer? Okay.
Yes.
Cool. Let me just make this float as well. I need to wait. How do I make this on top? Oh, you know, like menu bar. And okay, well, I guess I can't pin this to the top. Okay, well, I will pull this. HackMD is also on this side, or sorry, in the chat. So, I'm not gonna have it up constantly. If I'm gonna write anything in it, obviously I'll pull it up so you can see it when I'm writing. But yeah. So I guess I'm gonna be talking about async functions and traits and return position infiltrate in trait, which is the feature that async functions and traits is implemented via. Specifically, async functions and traits aren't very special. They are just extensions of return position infiltrate in trait, just like how async funds are just extensions of return position infiltrate. So specifically, I'll do an overview of how we desugar an async function. So for example, an async function that, you know, has some body. I don't really care what the body is. Just it always desugars into something that looks like and who returns an info feature whose output is the same pi that you declare in the signature of the function. So this is all a transformation that happens pretty early on in the compiler. And that means that all the type checking and all the kind of the deeper important parts of the checking the async function is basically just checking infiltrates, which makes things easier for when we're talking about extending them to async functions and traits because we don't have to basically implement 4 different features. We don't have to implement RPIT, AFIT, which is async function in traits, and RPITIT, and I guess regular async functions. We kind of just we get the desugaring, and the desugaring gives us async functions for free once we implement return position infiltrates and traits. So I guess then the question becomes like, why don't we have return position infiltrate in traits? Specifically, like what's special about RPITIT? So when you write code like this, let me make my HackMD slightly bigger. Oh, it's a screenshot. So when you write code that looks like this, why doesn't this currently work? And this has to do with the fact that infiltrates, specifically return position infiltrates, RPITs, they're opaque types is what we call them inside the compiler, and specifically they hide an inner type. So whenever you have a function that returns an RPIT, we in the process of checking the function, we infer what the value is. It's like what the type is that is behind the RPIT, and that is a single type. So for a generic function, like this, simple size, which is, I know, not a particularly interesting return position infiltrate, but it's useful for our example. This opaque type impulse-sized, I'll just call it impulse-sized number 0, is inferred to be I32, and that's one value that basically by the end of the compilation session, every return position infiltrate needs to have basically one type behind it. Now, I guess the question then becomes like, wait, I thought that you could return something like, or you could do something like this. Let's say impulse-sized number 1. as an input and returns t as an output. So this, for example, the the value that we infer for impulse size number 1 is still technically one type, even though you can give it any t. And this is because in Rust, we have this concept of type variables and type substitution. So even though technically this impulse size can be any type that is sized, depending on what the t is that you call for foo, the type scheme, that the generic unsubstituted type that we infer for impulse size number 1 is going to be one type, and that type is going to be t. And then when we call foo with some value of t that we're substituting it for, like we call foo with the turbofish of, like foo I32, then we take the impulse sized number 1 type, which is t, and we substitute in t equals I32, and that gives us our output of I32. So this is kind of different from the way that we need to treat traits, or say infiltrates and traits. Specifically, there is no basically like least common denominator type that we can make out of a impulse size inside of a trait, because it depends on what the impulse that provides that trait is. So for example, if we have, I'm going to take this example code and move it up. For example, if we have this trait foo, has fun foo, returns an impulse size, and we have one implementation, like impulse foo, and we have another implementation. Fill in the gaps like this. There's no way of taking basically this is a valid program with return position infiltrates and traits, but there's no way of taking this and inferring one type that we then substitute with return, we then substitute with substitutions, generic type variable substitutions, to get like an opaque type in this trait. In this case, we want to think of return position infiltrate and trait kind of more like associated types. So we can think of this code, for example, as being written with stable Rust, like so. So we can take the opaque type, turn it into an associated type. We copy all the bounds on the impl. That's implied, but I'll copy it over just for clarity. And then we fill in the type and so this is kind of more how we want to think about return position infiltrates and traits. This makes sense basically with the trait model, with the fact that traits basically declare that they have an extra an item, an associated type item, that then the impl is responsible for substituting what they or not substituting, but providing what they want their kind of the concrete implementation to actually have. So that's basically why infiltrates in traits don't come for free, because they act very different than both return position infiltrates and type alias infiltrates. I'm not going to discuss argument position infiltrates. Like argument position traits or infiltrates are like this. Because argument position infiltrates are also different, but they are the simplest because they are literally just sugar for generic arguments that you can't name. So you can always transform an argument position infiltrate into something like this. So return position infiltrates, which are stable, and type alias infiltrates, which are coming soon, both kind of have this one body provides the type. So basically someone provides the hidden type, and we do inference, and we find out what that hidden type is behind the scenes, and that's basically how we do it. It's basically just like a kind of another type of type inference, as opposed to infiltrates and traits. Return position infiltrates and traits are slightly different because they kind of act more like associated types. Now they do work like kind of like infiltrates in other positions, specifically because they still participate in inference. We don't want the user to have to provide what the concrete types are for their infiltrates, obviously, because then that would mean that why can't you just use an associated type? And also, it's not always obvious how to find out what that type is during the same stage of the compiler as other desugarings that happen, like async lowering. So yeah, that's just the background. So that's kind of how I want to frame the question, is like, why are return position infiltrates and traits so hard, and like why are they different? And those differences I'm going to kind of rely on to explain some of the complexity that I'm going to go into in the compiler. So all right, any questions right now from the two folks that are here? Cool. So I'm going to go from the top down, or I guess from the bottom up, or however you want to think about the. Oh, Santiago, you have a question?
No. I was working on this stuff, so I more or less know.
Yeah, of course, yeah. All right, so I'm going to go from the top down or the bottom up, or however you want to think about the compiler being laid out. I'm going to start from parsing. So specifically, how do we parse return position infiltrates in traits? So like all parsing, we have, I guess parsing specifically isn't that interesting, because the AST that we start out with when we parse some code that has an infiltrate in it just parses infiltrate, and basically when it parses infiltrate, all the infiltrates that you can see in the program are all the same. I said that argument position infiltrate's different than return position infiltrate, is different than type alias infiltrate, but during parsing, they all kind of get treated the same. It's the responsibility of AST lowering to distinguish these types of infiltrates and to do the desugaring from argument position infiltrate into generics, and to turn currently return position infiltrate and type alias infiltrate into these opaque items that we use for type inference later on. So I guess we can go into Rustc AST lowering /item.rs. And we want to look for infiltrate context, I think. No, it's not this one. Oh yes, it is this one. So when we're lowering code, we take AST and we turn into this kind of lower representation called HIR, or here. I'll call it here for the rest of the time. But we basically have, depending on the position that the infiltrate shows up in, that is what informs us how we actually want to lower our infiltrate. Specifically, when we're lowering the parameters of a function, we want to treat them like argument position infiltrates, or in this case, they're called universal, because there's the type theory kind of notion of universal versus existential. So we could probably rename this to arg position or something like that, but whatever. So then we basically pass this infiltrate context ITCTX down to the lowering code that eventually gets down to a function called lower tie, and then lower tie is when we actually do something special with the infiltrate that we see. But that's not interesting. We care more about the return type of the function. So this is lowering async items, I think. So let's look for other infiltrate contexts. This is lowering the type alias. When we're lowering a type alias, we give it the type alias opaque tie context, and that just tells the lowering code that that we want to treat it like a type alias infiltrate. We could gets its own item created and everything like that. So that's that. There are certain positions where infiltrates are disallowed. You're not allowed to put infiltrates inside of the types inside of a generic. Like you can't write something like can't write something like is into full size. I don't think you can write something like that. So there are a few positions where we disallow them and we pass something called an infiltrate position, which basically tells the error message that it's not allowed in generic positions or in closure parameters or closure return types and all this other stuff. More infiltrate. So I'm trying to find the infiltrate context for the ones that we care about. Return position infiltrate. Oh, no, it's not even used in this function or in this file. It's in lower assoc tie constraint. No. Let's see.
Are you looking where is
Yes.
RPITs are lower or?
Yeah, where RPITs are lowered. So it's in lower. So when we're
it's in lib in the lib file, there is a lower opaque.
Yeah, I got it.
Okay.
That's so yeah. This is the function that we use to lower a function, decal, which is the declaration part of a function. So it's everything except for the body, and we make a distinction between the decal and the you can use patterns to destructure inside of an argument. We don't care about those in the function decal. We only care about the types in the function decal. But this is lower fun decal. It is what lowers the signature of a function. And when we are in a function, depending on what the function kind is, we lower, we pass the different infiltrate context to. Specifically, when we're lowering the output, if infiltrate allowed is true, which is if it's a function, or if it's an inherent fundecal kind. I don't know what's an inherent fundecal kind. Do you know what an inherent fundecal kind is, Santiago? No. It doesn't matter. The one that we care about is the fundecal kind. It's for an inherent method. It's for impulse without traits. Right, obviously. Then return position infiltrates allowed in regular functions and in inherent methods. And then we have special checks for the feature gates for return position, infiltrate, and trait. And if that feature gate is true, then infiltrates are also allowed in impl fundecals, which are impls that have traits associated with them, and trait fundecals, which are the default bodies they're the signatures that show up in a trait. So yeah, where were we? We go. See what this function is called. Yeah. So we pass down that return position opaque tie infiltrate context, which tells the lowering code that when it sees an infiltrate in the return type of a function, then we want to create a new here item for it. So we create a here item for so I guess I should go into the board a little bit more detail. An item in Rust is anything that is kind of self-standing. So people think of items as things like functions and traits and impls and associated functions and things like that. But we also have we also treat opaque types as items because it's useful, because we do things like type check and infiltrate and stuff like that. So from a user perspective, we might not want to think of opaque types as items, but we treat them as items internally. And that's useful to know because all items have something called a def ID, and a def ID is a unique identifier for an item, but it also allows us to call queries on items and things like that. So yeah, that is that. So this is how we actually feature gate whether or not return position infiltrate is allowed. It's because we we basically, when we're lowering the return type of a function, we check if it's allowed, and it's either conditionally allowed for certain positions for infiltrate and trait, or it's always allowed if it's not, if it's a regular return position infiltrate. All right, so this is basically how we do the parsing, how we deny return position, infiltrate, and trait. Async fun and trait is somewhat similar. So whenever we have a async function, so let's go to somewhere where we call this lower fun decal. Trying to find out where we have an lower async fun. This one, for example. So whenever we parse a function signature, we parse that async keyword and we store it in this thing called asynchronous. So asynchronous is just in the header. There's a few other keywords that we store there, like defaults and stuff like that. But if we have asynchronous, then we pass down the fact that a function is async to this lower fun decal. And if we have async, then we match on this make ret async. And if that's true, then we do a very similar check. So we check if async fun is allowed. It looks just like the return position infiltrate allowed, but it checks a different feature gate because we have a feature gate for async fun and trait. And we lower an async fun ret tie. So this is just special because it injects an extra, an extra arrow fun, arrow future type. So even though the user didn't write impl future output equals tie, they just wrote arrow tie, we basically inject that extra impl future here. So this is basically the desugaring that happens. It's very simple desugaring. We just we do some lifetime stuff because async functions capture all their lifetimes, and we just generate an opaque type. Generate the opaque type for impl future. So
I think I have a question that I think
yes.
people may ask. I kind of have answers, but like I don't
Please
feel
do.
strong English to make it live. But you may know also, like one first like naive question is like you said that, for instance, that an async function it's literally like a function that returns impl trait, impl future, and then the return type. So like the naive question would be why like all this code structure doesn't end calling like lower opaque, like using the same architecture we have in the compiler. Like why don't we have a like kind of a pre-simple desugar for async functions and we special case everything there? I know that we also with lifetimes we capture different things, and that may be also the reason, but
yeah, that's I mean so it's because we capture lifetimes, we have to generate some extra where clauses that says that the lifetimes that we have outlive some like special async fun lifetimes that we because so the real desugaring looks something more like us. I'm pretty sure this is kind of where I'm not super familiar because I didn't implement async fun and trait, or sorry, async funds. But then we have this like lifetime bound on the impl because it needs to have some lifetime bound, otherwise it's static. And then we like all the lifetimes that we see in the signature, I think, have to outlive that future lifetime. So we get this kind of like least upper bound lifetime for all the lifetimes in the async. And then I guess, well, so to answer the question, it's like, why don't we do the desugaring kind of elsewhere in a more simple way? Is because this is really the first part of the first point in the compiler that we can actually inject this desugaring. We could, for example, do it directly in the parser, but it's hard to then like check that the right feature gates are gated, and also just because having this lowering during here lowering means that we can emit more descriptive errors and things like that. So this is kind of just the place that we put it. Putting it any lower would mean that we would have to duplicate all the extra, like if the desugaring happened later on in the compiler, then we would have to duplicate more code. So this is basically the sweet spot of like
right. So my very first, like when I saw this stuff, my very first like naive thought was like, well, but I know that we are not gonna do this in the here, like before the here.
Yeah.
let's do it in the here, but why don't we like transform, let's say, this into, like, the problem is that the existing code takes AST, but
Yeah.
but you
Yeah.
could think that if this would be like the sugar into here and taking that here in order to convert to a different or something like that. This was
Yeah.
kind of my naive thought, and I understood that lower opaque and all this stuff like works with AST, but yeah.
Yeah, I guess to answer your question is because we don't have the notion of a here transformation. Once we've lowered
Right.
here, that's all we get. So we have to lower from AST to here in one step. We can't even create any intermediates and do anything with the intermediates. So that's basically just the architectural limitation that we have to work with, that we don't have like a pre here. Ideally, we would have some sort of like kind of stages of lowering to kind of disentangle all the complications around lifetime resolution and things like early lifetime resolution and stuff like that, which we do kind of using the AST. That is like name resolution for this. It's like the reason why we know what like dispute actually means in this example code.
Yes.
But yeah, so that's basically why. And that's not really a question, I guess, for infiltrate and trait necessarily. But it does add some complication because infiltrate and trait has to be its own special logic. Or it has some quirks about its special logic, and it has to tie into all this other kind of not necessarily tech debt, but it is kind of the interesting part of the just the fact that we don't lower here in steps. All right. So that's kind of that. So at that point we have lowered things into here. So so that's just how infiltrate works. Infiltrate and trait is special because when I describe this desugaring here, when we turn the return position infiltrate and trait into an associated item, that's not currently how it works. So I'll go into detail about how it really does work. Well, actually, maybe I want to go into one more detail, kind of on the user perspective. So this is gonna kind of put a tab in what we're talking about right now. It's like, how do we want async front end trait and return position infiltrate and trait to work? Specifically, we want them to work like associated types. We want something like this to work. So we want this code to type check properly. The fact that the user can provide a more specific type from the infiltrate, as long as that the return type that the user is providing satisfies the bounds on the infiltrate. This is very useful because then then it actually does work like an associated type, because if you had the same code that did get lowered to an associated type, you would be able to observe the fact that for unit, the foo function returns I32. So that's just a desirable property that we want to have. Kind of a side note, but we want this code to compile. So yeah, that's just a side note. One thing I wanted to kind of talk about. But as I was saying, so this desugaring that I mentioned is not exactly how it works currently. In the future, hopefully it is how it does work, but we have some limitations, some major limitations on the way that we do lowering and the way that we do type checking. That means that this is not exactly how it works. Specifically, the way it really does work is that as I was saying before, that we lower these opaque types into things called items, and items form a tree inside Rust. So inside of a module, you have impl items and function items and stuff like that. Inside of an impl, you have associated type items and associated, associated function items and associated consts. And then in return, it's like return position infiltrates get lowered into opaque items, and opaque items are always children of the thing that declared the opaque type. So when you have a function that returns an infiltrate, the opaque type is a child of the thing that had the arrow return type. And this is because of this example that I gave earlier, the motivating example of the fact that the infiltrate that we lower has to inherit the generics of the type, or sorry, of the function that's being type checked inside. If this got lowered to a different item, then we would have to do something like copying all the where clauses and generics of the function into a new item. And as Santiago knows, that's not as easy as it turns out to be, because of the way that we do lifetime name resolution and things like that. As a side step to keep things simple and to make it possible for us to even have an implementation today, we currently lower infiltrates and traits, just like all other infiltrates, as a child of the function item that they're declared on. So we have something like this, the sugaring, or actually I'll just take the example code. We have something like this. Should I move this down to a better? Oh yes, move this down to it actually gets desugared to something that looks more like fake syntax of it. Okay, number 0 size is a so opaque number 0 is a child item of the function foo, which is a child item of the trait foo. But when we're talking about lowering impl blocks, we have a complication. Well, we have several complications actually, because for example, this first impl block that implements this trait foo, we don't actually nothing in the impl block actually tells us that we're implementing a function that returns an infiltrate in a trait. From this function signature, we see function foo returns a. From this impl block, we just see that we're implementing a trait. And that's a problem because if we were actually lowering things like an associated type, if we create an associated type on the trait, then we would have to satisfy the associated type by creating an associated type on the impl. Now, this is hard for two different reasons. One is that the return position infiltrate and trait can kind of be arbitrarily nested. So for example, this is valid code, and we want it to be valid code. For example, this. So for example, when we're matching up the function signature against the trait that it's implementing, we have to match up wrapper of unit against wrapper of impl size, and then match up unit against impl size. And this is kind of like a type system operation. This is not something that we typically want to do during earlier phases of compiler, because we don't have the type system machinery spun up to actually do this. We could technically do something like an easy example like this, but I'm going to give another example of something that's like literally impossible to actually check during like AST lowering, or during the next phase, which is right before we actually do type checking, called AST conv, which I can go into detail. So instead, let's assume that we have a nested infiltrate. So impl deref for whose target impl size, we return like a static reference to unit. So in this case, impl deref gets inferred to be a static reference to unit, but then target gets inferred to be just a unit. And this requires us to actually do like real trait solving, because we need to, one, check that that the static reference to unit implements deref, and then we too need to like find out what that target type is, which can be arbitrarily complicated depending on the way that you write impl blocks. Impl blocks are very general. You can write all kinds of weird where clauses, and you can match on all kinds of self types. So this is not something we can do just by like matching up the return type in the trait and matching up the return type in the impl, and like matching them structurally. We have to do something kind of deeper. We have to do something kind of more complicated. It's like a type level equality, which requires us to defer these questions of like, what are the concrete types that we implement for an RPITIT, to all the way to when we have the type checking machinery, which is pretty late in the compiler. I mean, it's still part of the front end, but it's pretty late in the compiler. It happens all after all of these desugaring steps. So that's the complication, and that's kind of what we're working with. So yeah, any questions up to this point? This is kind of the philosophical part of it. I haven't really gotten into the details, and I'm going to probably jump into VS Code and talk about the actual implementation. But yeah, questions? Cool. Okay, so let's dive into the nitty gritty. I'm going to talk about, I already discussed what an item was. I kind of discussed what a def ID was, but it's just an ID, a unique ID that we use to identify all items. And specifically, we use it to run queries on items. We can ask arbitrary questions about items, like what is the type of an item, and what are the where clauses on an item, and what is the generics on an item, and stuff like that. And then we have another kind of interesting question that I'll go into is like, what's a def kind? So def kind is an enum that identifies every def ID. So you ask, when you have a def ID, it's very generic. You don't know actually what it is. So the first question that you want to ask when you're implementing a generic query is, what actually did you pass to me? So we have things like structs, unions, enums, variants, and traits, and type aliases, and whatever. But whenever we lower a infiltrate in a trait, we don't use the regular def ID for infiltrate and trait. We use something called infiltrate placeholder. And this is just because of what I was talking about earlier, is the fact that infiltrates and traits aren't really opaque types. Asking the same questions about an opaque type and an infiltrate in trait doesn't really make sense. You don't ask what the type of a return position infiltrate in trait is. You ask what the type provided by an infil of that trait is, versus you can ask what the type of a regular RPIT is, because that, as I said before, that's just checking the body of the thing that provides it and finding out what the hidden type is. So we use this infiltrate placeholder def kind to switch on a lot of code during type checking, to specialize the implementation of checking and doing all the kind of query stuff with return position infiltrates and traits, just because the questions and how we answer them are slightly different. So just keep that in mind. I'm going to be discussing the infiltrate placeholder def kind in a few other places. And then, as I said before, also, so some of these queries that we can ask about infiltrates and traits, like what are the generics of an infiltrate in a trait? What's the type of? So the type of query, for example, returns the unsubstituted type of anything that has a type. It'll crash if you ask it like what the type of a mod is, for example. But functions have types. It's their type signature. Associated types have types. It's like the thing that happens after the equals in, type X equals Y, things like that. Struct fields have types. Yeah, questions yet? Okay, so I guess maybe I could come up with a motivating example. So how do we? Okay, yeah, sure. Break. So let's ask the questions. How exactly do we type check this function? Or sorry, this program. We have a few different things that we want to answer. Like one is we want to check that it's valid. So we want to like know what the value of all the infiltrates are. And we want to be able to like, I guess those are like the two questions. I don't know if there are any other meaningful questions to ask about the program right now because we're not actually using it for anything. But yeah, let's see. I don't know what the best way of approaching this is. So I guess maybe we can go down these. We did lowering. So once we've lowered everything into here, we want to actually like lower it one more time into the representation that the type checker uses. This is defined inside of Rustc middle tie, the tie module inside of Rustc middle, and it has a few different names depending on who you ask. I call it the type checker level. I think Nico calls it Chuck. Different people call it different things. Some people just call it middle. Middle's also a great name for it. And this happens using something called AST_conv. So let's go to AST_conv / mod, and let's see how we actually lower a. So this is how we lower an opaque type. So whenever we ask the question of we have a here tie, for example, in this function signature, we want to know what its actual type is. We have to give it to AST_conv and it gives us back a tie. So that's the signature of this function. We give it a AST tie and it gives us back a tie. So we can look into what infiltrate tie to tie looks like. So this is a function that's just specialized on lowering an infiltrate specifically. And I guess what's interesting is that in order, like when we introduced RPITIT, we added this extra Boolean that we switch on called intrait. So if a function, or sorry, if an infiltrate is intrait, then we lower it using one logic, and if it's not in a trait, then we lower it in the other. The only place it's actually used is that it depend like what kind of type we actually return. What kind of type we actually return depends on whether the opaque or the infiltrate shows up in a trait or not. So if the infiltrate does not show up in a trait, then we just treat it like an opaque tie, which is we don't normalize it, which means we don't reveal its inner type until after code gen. It has special logic for infiltrates always implement the traits that are defined on it. But if we if it's inside of a trait, we lower it like a projection. So projection is the name that we use for associated types internally. So when I said that we don't actually lower things to associated types, I was only kind of right. We lower return position infiltrates in traits like projections, except for the fact that they don't actually point to like an impl, or it's like a type X item inside of a trait or an impl. They still use the dep ID of the opaque. And this is important because there is no that we don't actually generate an associated type inside of the trait for an infiltrate. So but the fact that we lower it like a projection means that all the type checking code treats it like a projection, which is pretty much what we want it to be treated like. We want it to get normalized during regular type checking. We take associated types and turn them into if we know what their like real value is, we want to actually do that process called normalization. Versus opaque types, that doesn't happen. So instead of having to add all the logic of normalize an opaque type if it's an infiltrate trait, but not if it's a regular opaque type, we could avoid all that by just treating like a projection type. So how do we actually normalize this projection type? So that's the question. It's like when we have code that looks like this. Well, let's see. how do we want to do this? Yeah, let's just say equals. Let's do, how do we actually normalize this impl deref that we see in the trait signature of trait foo? And this happens inside of projection. So the projection. I guess in the meantime, any questions? Cool. So Santiago, yes, no?
No, I was going to say no, but just but anyway, maybe for the recording purposes,
Yes.
like if you can go back to the example that you were writing. Maybe you already said this, but I guess that it may be important for the like architectural point of view of how things are connected. So from what you said, like basically like people can think that this from in the main function, like you have the LED and that projection.
Yeah.
So that at some point is parsed. You went through the AST to here lowering. Then there is middle, and in middle we convert that into a projection.
Yeah.
So, like, I always wondered, like, when I was starting to go to Rust specifically, I always jumped into certain areas of the code. I never knew how the rest of the stuff were connected, you know. So I guess in this sense you're doing a good job of explaining this, and what I'm wondering is like after that, like after the middle, like what, like if you can explain what will happen with the stuff
after middle.
Right, after the middle, when we converted this to projection, like what is next, let's say.
So I guess what happens in specifically in function main is this is a function call. Function calls for traits specifically. They take the trait signature that has been converted using ASTconf, and so the type of this expression right now is going to be let's call this outer infiltrate. Let's call this opaque 0. 0. And let's call this opaque 0. The inner one can be called opaque 1. I don't think we're actually going to even touch it. But let me make this a little bit bigger. 1. And I guess so. Let's maybe go into some of the weeds here. Specifically, opaque 0 is a generic type. It is generic because it inherits the generics of function foo, and function foo is generic because it inherits the generics of trait foo. And you might ask, trait foo is not generic, but traits always have one extra generic that you can never see. It's called the self type. It's always generic number 0. So this has, I will put the generics of opaque 0 after it. It has a generic type self. So, and this is useful because I'm going to be going into how we type check this function or this statement right here. Same thing, I guess, for opaque 1 also has generic. If we had like a T here, then it would also inherit T and it would have 2 generics that we would have to substitute later on, but we don't. So we have 1 generic. So when we're type checking this method call, this is a method call, specifically a trait method call, we take the signature and we instantiate it for the generics that we have given it. So we could kind of transform this into something that looks more like this. So this is kind of what it looks like if foo was not using this universal call or trait call syntax or whatever, where the self type is the first generic of the function foo, or what's a generic on the trait. So we instantiate this function signature, we get its return type, and the return type of this is going to be a projection. So it's going to look something like this as foo colon number 0. That's, well, it's number 0, which we don't currently have normalized. This is just like if we had a function that returns a projection type. We need to then normalize this type, because if we try to equate this type against this type, they don't equal each other. So we need to normalize both sides. So we're asking the question of whether we can equate this, because that's how assigning to a variable works, that the type needs to equal the thing that you're trying to assign it to. Technically, it needs to be like a subtype of the type that we're assigning to. We don't have to care about lifetimes here. So which is the only type of subtyping we support in Rust. So in order to answer this question, we have to normalize this projection type. And that leads us to, because as I said before, when we do the ASTCon, which is the conversion of this function signature, the return type turns into a projection type because it's inside of a trait, so it doesn't turn into an opaque type. But if it turned into an opaque type, it has different rules. It doesn't get normalized, and if we try to assign that to some concrete type, it's going to fail. But because it's a projection, we have one chance to save ourselves, and we can project this type. So let's go into the projection logic. Do you think this is a good place to jump into projections, Santiago, or do you want me to go into more detail?
Yes, no. This is a great explanation, I think.
Thanks for getting me to. I didn't really know how to segue into this, but this is probably a good example. So project.rs, we have I'm not going to go into the full projection logic. I'm going to start with project. Yeah, this is a good place to jump into. I'll minimize this. So project is the function where we give it a projection tie obligation, which is just an obligation is a type that wraps something and a parameter environment, which is a bunch of where clauses and some tracking information for like what caused this obligation to be created. But specifically, we only care about this part of the obligation, which is the projection tie part of it, because we're trying to normalize a projection tie. So we have a projection tie, which is a def ID, as I said before, and some substitutions, which is those generics I was talking about. In this case, the def ID is going to be the def ID of the opaque number 0 on this trait, and the substitutions are going to be this list that I said before of the self type. In this case, the self type has already been inferred to be unit. If I don't know if people have watched LCNR's thing last week, but I won't go too much into detail about exactly how candidate assembly works. But we have a few different ways of normalizing a projection type. Specifically, a projection type can come from a where clause in the paramev. It can come from a din type. It can come from a lot of different things. So we have all these different candidates that can possibly satisfy the question of how do we normalize a projection type. None of these are sufficient for our purposes, because all these assume that the items that they are normalizing are regular associated types on a trait. So we had to add another assemble candidate for infiltrates and traits specifically. Now we can jump into what this does. So we just pass down the projection tie. We pass down this thing called a candidate set. That's just how we accumulate the different options of what can satisfy a projection. The first thing we do is we check if the def kind is an infiltrate placeholder. That's the type that this def ID opaque number 0 has. So we don't want to try to do RPITIT logic on a regular associated type. So this basically short circuits the logic if it's not an infiltrate placeholder. If it is, then we want to look at what the trait is, or sorry, the trait function is that is associated to it. So trait from def ID would be, in this case, the def ID for this function foo on the trait. This is some special logic. I'm not going to go into it right now, but this is some special logic for default bodies on traits. So you're allowed to write, for example, in like can write. So you can write like, I don't know what to put this. You can write this. You're allowed to provide a default body on a trait, which gets provided by default on impl blocks that don't mention the function foo, and that won't be an error because there's a default. We want to support that for RPITIT as well. It's just that the rest of the logic that I'm going to talk about assumes that we're inside of an impl block, or sorry, that we're normalizing the projection whose self type is a concrete type provided by an impl block, and trait defaults don't work like that. Their self type is the default self type that I mentioned up here. It's basically just like an unsubstituted parameter, like if I said no. So I won't go into this. The check here is just like if the projection has a self type that is the default self, then we treat it like an impl trait in trait default body candidate, and we short circuit. We don't have to do any extra checking. If we do, if we're not inside of a default trait body, then we get the function's def ID, then we get the parent of that function, which is always a trait. We get the substitutions for that trait, which basically chops off any extra generics for the trait method. So we just get all the generics for just the trait, because that's all we need for this next question that we're asking. So it's a self type and all the generics listed on the trait directly. And we want to ask the question of whether or not we know that that trait is being satisfied using a impl block. Now, I'm not going to go too much into the detail of how select works, but if select, which is the thing that tells us how specifically we implement a trait, returns a user-defined impl source, which is basically an impl block, then we know that we can project it onto a concrete type, because we can look at the impl block. If that trait gets provided with anything other than an impl block, then we mark it as ambiguous. We mark this candidate as ambiguous, and we say we don't know how to normalize this type. So for example, if we had something that looks like where T is foo, we want to like normalize this is foo. We don't know how to turn this into a concrete type. So when we try to project it onto a concrete type for this impl size, we don't know how to do it. We mark it as ambiguous, we give up, because the thing that provides this, basically the thing that witnesses the fact that T implements foo is not an impl block, it's a param candidate, a where clause. So once we've assembled our candidates, either our default trait body candidate or impl trait and trait candidate, where we store the data, tells us what impl specifically provides this trait and what the substitutions for the impl are, because impls can have their own generics, and those generics don't need to line up with the trait's generics. Then we finish candidate assembly. All these other, trait def, object tie, and assemble candidates for impls don't apply to RPITITs, and assemble candidates for param also doesn't, at least for right now. In the future, you might be able to do something like T is foo, where foo, the method, returns I32 or something like that. But that's not currently valid syntax. In the future, that would be provided by assemble candidates from param, because this is a param candidate. And in the case that we have one thing that unambiguously provides the projection, which in this case we do, we confirm. So we jump into confirm, and we basically run the same logic, where if we see that the projection candidate that provides the impl trait and trait, that provides the projection is an impl trait and trait, that we confirm it. So we want to take that data that we collected in the during that select, specifically with impl source data, which has useful information like the impl def ID, the subs, and then the nested predicates. So impl blocks can have where clauses on them, and we need to check those where clauses are true before we do the projection. So we need to finish out this confirmation. So we let's see. So again, we grab the traits. We grab the trait function that provides this infiltrate and trait. The reason we do this using a special infiltrate and trait parent function is because if we're asking, if we're trying to normalize, for example, this inner opaque type, the parent of this inner opaque type is the outer opaque type. So if we just got the parent, we tried to ask all these questions about, like, you know, the thing that provides it on the outer opaque type, then it's going to fail. So we want to unwrap all the layers of infiltrates that we are currently wrapped inside to just get the item that we care about, the function, which the function is the thing that's responsible for providing, is the thing responsible for providing what the actual concrete type is that we're looking for. Right. Any questions before I jump into the actual confirmation logic? Cool. So once we actually have the trait fun that gets provided by, so this is the function on the trait, to be specific. This is not the function on the impl. To turn the function on the trait into the function on the impl, we call this function called a soak def. That goes through this specialization tree. So you can have specializations on impl blocks and more specialized impl blocks and stuff like that. This is not specific to infiltrates and traits. This is actually the same logic that we have to go through for regular associated types. So I'm not going to go into too much detail, but we call a soak def. We get the thing that actually provides the most concrete implementation of the function that we're calling, and we make sure that that actually has a value associated with it. If not, then we throw an error. I'm going to jump over the default body logic, but now we actually know what is the impl block that provides this, that should be providing the infiltrates that we're looking for. We want to turn the projection substitutions that we have, basically this list of substitutions, which for this example is kind of puny because it's just a self type, into we want to rebase these substitutions onto these substitutions of the impl block. So for example, in this case, the impl block has no substitutions. There's no generics or anything like that. We could technically have substitutions here, but in this case, when we rebase these substitutions from the trait subs onto the impl subs, we end up getting an empty substitutions list. So now we have impl number 0, : like number 0, and those subs are nothing. I really should be putting the function here. It's a function. I don't know if y'all want me to go into an example that actually has like subs on the functions and on the opaque, but rebasing substitutions isn't particularly relevant to RPITITs. It's something that happens all over projection code. So speak up or forever hold your peace. Okay. But all you really need to know is that when we do this rebase, now we have the substitutions in the worlds, in the universe of the impl. So if we took a generic type anywhere in this impl block, we give it the substitutions that we now have, which is an empty substitutions list, then Rustc will be happy. And so I guess then the only interesting part is now we need to get the predicates, the where clauses of the impl function, because in order to call the impl function, and therefore in order to create one of the opaque types on the impl function, we need to like check its where clauses. And then we need to get the actual opaque type. So as I said before, finding out what the hidden opaque type on a impl block that provides an RPITIT is kind of hard. It requires us to do type level equality, type level kind of equation of types. We can't just look at the types and match them up structurally. So this is actually the responsibility of a query called bound trait infiltrate ties. And this is provided by a function called collect trait infiltrate ties. And what this does is I can jump into the query. I'll show you the what it does is it takes a key, which is a method's def ID, a method on the impl specifically, and it returns a mapping from the def IDs of the opaques to their concrete or to their unsubstituted concrete types. So whenever we want to know what the hidden type of a def or of an opaque type is, we get the function that owns that opaque type, and we ask to collect the trait infiltrate ties on that function. And the way we do this is by we compare an infiltrate signature against a method trait signature, or sorry, an infiltrate signature against a trait method signature, and we infer all the hidden types in the process. So I can jump into that code and explain exactly how it works. But maybe I can give a motivating example. So what would happen if we run collect infiltrate or trait infiltrate ties on this foo def ID, for example? Well, from a high level perspective, we want to basically take the function, the method signature, and we want to equate it against that must be great. So we want to run first through this kind of in the abstract, and then I can talk about this in the in like reality. So for example, this is what the trait has. This is what the impl has. So yeah, when we equate these two types, or I guess when we equate this opaque type against the infiltrate that we see, or sorry, the concrete type that we see in the impl, this is actually really simple because we just infer impl deref to be tick static. But how do we infer what this inner opaque type is? The only way we can do that is by checking the projection of this impl deref. So, for example, checking like what % fixed static unit as deref : target normalizes to, which is unit. So, and we only get this by checking checking that this impl deref is valid. It's valid only if target provides something that implements impl-sized. So we do this by walking through this infiltrate, and every single time we see an infiltrate, we substitute with an inference variable, and then take all of its where clauses and kind of walk those recursively. So I guess the way we actually really do this is by first, when we see impl deref whose target is impl-sized, we substitute that with like an inference variable number 1, and then that has the where clauses of number 1 is infiltrate number 1 is deref, and number 1 as deref. Target is impl-sized. So that's the first step of the process, and then we recursively walk both of these where clauses to see if we have any more infiltrates. So we do in this infiltrate, or sorry, in this where clause. So we then take this and substitute it. So number 2 is sized. And we turn that into equals number 2. So now we have kind of 2 things that we're required to prove. Well, and also we need to prove that the top level goal of this equals unit. Right. So now we have 3 different, I guess our goals that we are left over with are number 1 is static. Number 1 is deref. And number 1 is deref target is 2.
Just a minor comment.
Yes.
I think you wanted to write it like this.
Yes. Yeah, you can fix it. I'll move it.
Oh, sorry.
Yes, okay. Yes, you're right. So one more. But yeah, so
you were
okay.
testing us to see if
Yeah.
we were paying attention.
Not really. So I guess it might be interesting to talk about why I wrote it like this as opposed to writing it like this. Is that this is how the Rust compiler treats a clause with associated type bounds. It treats it as 2 different things. It treats it as one is the trait. So whenever you say that something impulse deref whose target is impulse sized, you say that thing needs to implement deref, and that thing's deref projection tie called target needs to then equal the thing that comes after the equal or after the equal.
So Michael, so collect trait input trait ties generates all these things through inference variables and yeah, okay.
Yes, yeah. So yeah, I can go into the code right after I kind of walk through this example. It might be easier to see what the code's doing as opposed to what I'm talking about, but I at least wanted to say that when we're asking the question of we need to equate impl deref whose target is impulse sized and tick static unit, this is what we get out. We have to prove that that tick static of unit needs to be assigned to some impl, or sorry, in some inference variable. The inference variable needs to implement a trait, and then that projection needs to be equal to another inference variable. So when we solve these, then we know then we infer that number 1 is tick static unit, and then if you'll know the built-in deref implementations in the standard library, you know that when you substitute tick static of like a static reference to unit into number 1 and then normalize this deref as target or as deref : target, then you just get the thing that is inside the reference type. So then we know that to its unit. So then we use these, we map them back to their infiltrates, and we use those to do the projection that I was talking about later. So we end up with a mapping that says that opaque number 0 is tick static unit, and that opaque number 1 is unit. And if it turned out that you provided a type that didn't actually, for example, implement deref, then we want to raise an error. For example, if I had this function signature up here, return I32, we want to say I32 doesn't implement deref. So let's actually jump into the real code, which is kind of hairy, but it's very similar to the code that we used to just check that that an impl method signature and a trait method signature are compatible. It's actually mostly cribbed off of that code, except for it does less stuff because it doesn't need to be as general. All it needs to do is just enough work to actually do the impl trait inference. So we get the associated item for the impl, we get the associated item for the trait, we get the trait ref, which is everything. It's basically the for an impl, the trait ref of that impl is it's just the where clause form of that. So the trait ref for this impl would look like unit impl. So that's the trait ref for this. And we get the param of the method. And the param is what we use. It's the word clauses that we're going to use to solve all the other questions that we ask inside of this thing. We do some bookkeeping, like we set up, we grab the return type spans. We can point at the return type if there's errors. We set up an obligation cause, which is basically just some bookkeeping that we use to give more useful errors later on. We do some bookkeeping with some substitutions to turn the traits method and the impulse method into something that we can directly compare to each other. I don't really want to go into detail, but just know that we're using those substitutions to basically instantiate the trait signature and then the impulse method signature basically into the same language, because they use different generic types, they use different substitutions and everything like that. So we need to basically substitute them in such a way that they then can be compared using just plain old type equality. We normalize those signatures because they might have projection types in them. And then I guess the interesting part is this thing called the infiltrate and trait collector. So the infiltrate and trait collector is what I was talking about, is where we recursively walk through the return type, and we collect all these where clauses, and we insert inference variables for all the opaque types. So let's see how that actually works. So an infiltrate and trait collector, like many things in Rust, implements something called type foldable, or it implements something called type folder, which means we can use it to do a recursive walk over anything that implements a trait called type foldable. And we override a function called fold tie, which lets us do something depending on, or we do something for every single type that we see. So if we end up, we run this on the return type specifically. So for the return type, when we see a projection type whose def kind is an infiltrate placeholder, as I said before, infiltrate placeholders are RPITIT, or the way that we represent RPITITs in def IDs, and we lower them to projections instead of opaques. So when we see a projection who is an RPITIT, then we want to check this mapping that we have to see if we've lowered it before. If not, then we create a new type variable. Just an empty type variable. We insert an entry for that return position infiltrates def ID and the type variable that we created, and we basically return, instead of returning the projection that we saw, we return an inference variable instead. And then for all the where clauses, or all the item bounds on the opaque type, we then want to instantiate the where clauses and recursively walk using the same folder. Normalize, and then register the where clauses that we see as things that we need to then later prove. And then once we've done that, we have then queued up all the things that we need to do to satisfy the infiltrate, and we return the infiltrate. So then at return position, infiltrate is now substituted and no longer shows up in the signature. Otherwise, we just kind of keep on folding. Any questions about this specifically? Cool. And as I said before, the reason why we have to walk through these the bounds on the infiltrate is that sometimes the only way that we can infer a nested infiltrate is by looking at its bounds. So for example, if we didn't walk through this where number one as the ref's target is impulsized, then we wouldn't have enough information to infer what the hidden type of the impulsize is, because it only shows up in the where clauses of this of this opaque type. And by where clauses of the infiltrate, I mean all the traits that come after the impl. Those are the predicates of the impl, which is basically the where clause of the impl. what else? So yeah, so now we have everything substituted with inference variables. We go back to where we call it. So we've collected all the types. That is our trait signature. That's our trait signature. We equate the trait signature against the impulse signature to cause us to start off the process of inferring all the infiltrates that show up in the signature. Then we kind of process all the obligations that we've seen, which causes us to infer all the things that only show up in where clauses. Hopefully by the end, we have fully resolved all the types that we're looking for. And I'm not going to go into some of this detail because there's kind of really hairy. You can see this is like 20 lines long of comment. Some really hairy logic about how we treat lifetimes in opaques. But by the end, we end up constructing a map that takes the def ID of the opaque type to the unsubstituted type that we want to then use later on in projection. And if that fails, we return we substitute tie error, which is the error type for that type. And then we arena allocate that map and we return it, and that becomes the result of the query. So then this map will have, for example, in this example, this map will have two entries. So it'll have the entry for the outer opaque, and they'll have the entry for the inner opaque. And we can use that to project either the outer opaque or the inner opaque, depending on which one we're asking a question about in type checking. So back in projection, we grab the bound trait infiltrate ties, we give it that impl function, def ID. We look inside the map to see if we have something that points to that, return position infiltrate def ID. If not, then we return tie error. We substitute it using all the the generics that we have. If, for example, that impl block was generic or the function was generic, and then we return that out just like every other projection type. And that's what causes us to then be able to project this infiltrate opaque number 0 into something that can be equated with the type that we expect it to be. Any questions?
One thing that surprised a bit to me when I saw this the first time is this Rustc here analysis, like place where the compare method lives. Mm-hmm. And I'm not sure if this is something new, but like not this code, the other part of the code that you were showing. I think it's the compare methods file probably.
Compare method has been here forever. LCNR just recently renamed Rustc here analysis from Rustc type check.
Okay. Yes.
And then LCNR renamed it this morning to Rustc here type check. So, but this, as I said before, this
I see. Yeah, analysis, seemed to me like something different. But yeah, now I understand better.
Yeah. So, collect trait infiltrate ties is the only thing that I added. And I said before that collect trait infiltrate ties, it has very similar logic to the other function called compare predicate entailment. Compare predicate entailment, somewhat of a misnomer. It really should just be called compare method signatures. What it does is it compares the method signature of a trait against an impl. It's the thing that if you write your impl method wrong, it will tell you, I expected this to look like this instead.
Yeah, like again, something really naive was that we're already type checking. Why are we going back to here? Like this was kind of the naive thought that it gave this, like given the name, this Rustc here analysis. But yeah,
so it is
back.
Like we are type checking, but we're not type checking in the same sense of when we talk about type checking, it means like we have a fresh body. We're checking expressions. We are collecting like region predicates and stuff like that. All that stuff happens inside of like a function context, and we don't have a function context here.
Right.
The only
Right.
checking we're doing is just checking that we need to do, because we need to process obligations in order to do the full general opaque type analysis. As I said before, if you have a nested infiltrate inside of inside of a binding of another infiltrate, then we need to process obligations, but it's possible for that obligation to return an error. So there is some checking, like inevitably there's some type checking going on or some trait solving going on, but that's not the responsibility of the method necessarily. It's kind of just a side responsibility.
Yes, I see.
Nobody else is throwing an error. If for example I had this is somewhere where we would want to have an error. Let's macro struct wrapper T. Not a wrapper. Body returns A32. So in the process of equating wrapper of impulse sized, or I guess if we're talking the logic of after we've run this infiltrate collector wrapper of some inference variable number 1, we try to equate that against I32, that's going to fail. So there is some type checking going on, but we're not checking expressions, for example. And we could move the logic that actually raises an error for this case somewhere else, but it would be kind of redundant. But this is something we obviously want to raise an error for. I32 does not equal, like there's no way of equating this syntax, or sorry, this type against this type and learning anything meaningful about impulse sized, because I32 isn't a wrapper. You would want to fix it by changing the wrapper of I32, and then that's when we infer number 1 equals. When we infer number 1 equals I32. So, yeah. Anything else? Any questions? So that's basically where all the special stuff ends. We treating or projecting return position infiltrates and traits is basically the only, like once we've gotten to that point, once we've projected it, then everything else after in type checking falls out kind of naturally from this. It's very front loaded. Everything in type checking and projection is kind of where all the special stuff happens. And then once type checking knows it's a projection type and knows how to treat it like a projection type, then we get everything. We know how to check expressions that return RPITITs. We know how to do mirror building with RPITITs. We know how to do code gen, because code gen just normalizes the types and reveals the inner types and stuff like that. Monomorphization, all that stuff comes for free. So that's all I think I have. I can go into more detail about anything in particular. But other than that, I feel like I just need questions. Other than, it is pretty hairy logic. It's very complicated because it's kind of in the middle of, we're in this kind of middle place where we treat RPITs. It's kind of like projection types and kind of like opaque types. And hopefully we'll be refactoring the code. Santiago will be refactoring the code to work more like an associated type. We obviously need to do some stuff still. For example, even if we changed these opaque items whose parents are currently, where did my opaque items go? These opaque type items currently have the parent is this function foo. If we change that so the parent is the trait and we treat it more like an actual associated type, we still have to do this collect trait infiltrate ties, for example, because we still don't want the lowering to have to find out what the associated types real concrete values are. This is not possible, as I said before, because we have to invoke the full type machinery in order to actually infer what this is. But it does mean that we probably can remove the special projection logic, because we don't need to because we already have projection logic for associated types, it means that we can remove some special checks around error reporting. Basically, everywhere where we currently have a check for death time is infiltrate.
Or the placeholder, yeah.
Except for, I mean, a few of them we still need to keep, like collect, infiltrate, trait, or collect, infiltrate, and trait, but most of them we can remove all these special checks, like what is this? Rustc tie. Oh, never mind, ignore that. Like closure, the way that we handle closure error reporting, for example, or that is the one way that we do need, or checking return position, infiltrate, and trait bounds. What is this actually? Oh, this is checking that it's well formed. We might need to keep this, whatever. But it does very dramatically simplify the code if we treat it just like a regular associated type, because that's mostly where the hairy logic that I just talked about for the last hour and a half has come from. All right, well,